Everyone asks the wrong question. The question is not, where did Earth's water come from? The question is, why is there water here at all? Because there shouldn't be. When Earth formed 4.5 billion years ago, it was a ball of molten rock. Temperatures at the surface exceeded 1,000 degrees Celsius. The planet was being bombarded constantly, rocks the size of cities slamming into it at tens of thousands of kilometers per hour. Nothing delicate could survive on a world like that. Not ice, not molecules, not anything that was wet. Water boils at 100 degrees. At 1,000 degrees, it doesn't exist at the surface. So the logical conclusion, the obvious one, the one scientists held for most of the 20th century, was that Earth formed bone dry, a hot, sterile rock. And then, at some point later, something brought the water. Something from somewhere else. That idea launched one of the longest, strangest detective stories in science. Decades of spacecraft, billions of dollars, probes chasing comets across the solar system, scientists arguing in journals, models being built and demolished, all to answer one question. Where did the water come from? The short answer, nobody knows for certain. The longer answer is more interesting, because the leading candidates are all deeply strange. And the newest evidence, published in 2025 and 2026, is overturning theories that scientists held for years. Before getting into theories, consider the scale of what needs explaining. Earth holds 1.386 billion cubic kilometers of water. That number is almost impossible to visualize. So here is a different way to think about it. If you took all of Earth's water, oceans, glaciers, rivers, groundwater, clouds, everything, and compressed it into a perfect sphere, that sphere would be about 1,385 kilometers in diameter, roughly the distance from Istanbul to Paris. 97% of that water is in the oceans. The oceans cover 71% of Earth's surface and have an average depth of 3.7 kilometers. The deepest point, the Challenger Deep, sits at 11 kilometers below the surface, deep enough to drown Mount Everest with room to spare. All of that water, all of it. On a planet that, by all rights, should have formed without a drop. And here is the thing that sharpens the mystery. Mars doesn't have oceans. Venus doesn't have oceans. Mercury doesn't have oceans. Earth is the only rocky planet in the inner solar system with liquid water sitting on its surface in massive, stable quantities. Why Earth? Why not the others? That question has no clean answer. But the search for one reveals something strange about the history of this planet and about where water in the universe actually comes from. For most of the late 20th century, the dominant theory was comets. Comets made intuitive sense. They are mostly ice. They orbit the sun in the far outer solar system, in a structure called the Oort cloud, or in the Kuiper belt beyond Neptune. Early in the solar system's history, gravitational perturbations, mostly from the giant planets, Jupiter and Saturn, sent comets hurtling inward. Some of them hit Earth, and when they hit, they deposited water. A comet impact delivers water the way a snowball delivers snow, violently but effectively. The theory had elegance, it had simplicity, and for a long time it had no obvious competition. Then the spacecraft started arriving. In 1986, the European Space Agency sent a probe called Giotto on an ambitious mission: fly close to Halley's Comet and measure what it was made of. It was the first spacecraft to get a close look at a comet's nucleus. What it found was significant, not because of what it confirmed, but because of what it did not. Giotto measured something called the D/H ratio. That is, the ratio of deuterium to hydrogen in the comet's water. Deuterium is a heavier form of hydrogen, the same element, but with an extra neutron in the nucleus. This matters because water with a higher deuterium content forms in colder environments, farther from the sun. Earth's oceans have a specific DH ratio. That ratio is essentially a fingerprint, a chemical signature that can be traced back to where the water formed. If comet water matches Earth's water fingerprint, comets are the source. If it doesn't, they're not. Halley's Comet's water didn't match. Its deuterium ratio was twice that of Earth's oceans. Then another comet. Then another. Most Oort cloud comets showed the same mismatch. The water was real, but the chemical signature was wrong. Comets that formed in the deep cold of the outer solar system tend to carry heavier water, more deuterium, than the water sitting in Earth's oceans. There was one notable exception. A comet called 103P/Hartley 2, a Jupiter family comet, one that formed closer to the Sun than Oort cloud comets, had a DH ratio remarkably close to Earth's. Scientists got excited. Then came Rosetta. The Rosetta spacecraft, launched by the European Space Agency, spent years chasing comet 67P/Churyumov-Gerasimenko. It arrived in 2014. Its Rosina instrument measured the comet's water in detail. The D/H ratio it found was 5.3 times 10 to the minus 4. Earth's oceans measure 1.56 times 10 to the minus 4. The comet's water was more than 3 times heavier than Earth's. Comets fell out of favor, but then, in 2024, a team revisited Rosetta's original data. They found a problem. During the measurement, the spacecraft had been flying through a dust cloud that may have contaminated the readings. The comet itself might have had different water. And in 2025, observations of another comet, 12P/Pons-Brooks, detected a D/H ratio much closer to Earth's oceans. So comet theory was not dead. It was just unclear. The chemical fingerprint was inconsistent. Some comets matched, some didn't. This meant either comets were not the primary source, or the solar system's comets are more diverse than scientists thought, some carrying Earth-like water, others not. The comet story is still being written. When comets fell out of favor, asteroids stepped in. Asteroids are rockier and drier than comets, but they are not completely dry. A specific class of asteroids, carbonaceous chondrites, sometimes called C-type asteroids, contain significant amounts of water locked into minerals as hydroxyl groups. These asteroids form in the outer asteroid belt and can hold water in hydrated silicates, even in conditions that would destroy ice. And carbonaceous chondrites have a D/H ratio very close to Earth's water. That match was compelling. Scientists also noted that asteroids hit Earth far more frequently than comets. During a period called the Late Heavy Bombardment, roughly 4.1 to 3.8 billion years ago, though the timeline is still debated, the inner solar system was peppered with impacts from objects that had been gravitationally disturbed by the giant planets. If a significant fraction of those impactors were water-rich asteroids from the outer belt, the delivery math worked. The asteroid theory became dominant. By the 2000s, most planetary scientists would have told you that Earth's oceans came primarily from asteroid impacts. Then the problems started showing up. In 2023, researchers at Woods Hole Oceanographic Institution and collaborating institutions analyzed a set of melted meteorites, objects that had been through extreme heat, either from collisions or from sitting close to a young sun. These melted meteorites, called achondrites, had extremely low water content, almost nothing. The melting had driven off their volatiles. This mattered because if Earth's building blocks had been through such heating processes, as the inner solar system's rocky material certainly was, they would have lost most of their water during formation. The raw ingredients Earth was made from might not have contained much water at all. A 2025 study from Oxford, which analyzed a different class of primitive meteorites, reinforced this. The material that built Earth may have been rich in hydrogen, but poor in intact water molecules. The hydrogen was there, locked in minerals, in iron compounds, in sulfide structures, but not as the water molecules that eventually filled the oceans. So if Earth's building blocks started hydrogen-rich, but essentially dry, and if many of the asteroid impactors were too heated to deliver significant water, where did the water come from? In 2023, scientists at Carnegie Institution for Science published a theory that changed the shape of the question. Anat Shahar and her colleagues proposed that Earth might not have needed water delivered from outside at all. Instead, water could have formed right here, inside the planet itself, during the chaos of its early formation. Here is how. When Earth was young, it existed inside a solar nebula, a vast cloud of gas and dust surrounding the young sun. The most abundant element in that cloud was hydrogen. In the earliest stages of planet formation, the young Earth was wrapped in a thick hydrogen atmosphere, drawn in from the surrounding nebula. At the same time, Earth was a magma ocean, a global sea of molten rock, hundreds of kilometers deep, churning at temperatures that made the surface of Venus look temperate. Hydrogen plus iron-rich magma plus extreme pressure. These three things, combined, can produce water. The chemistry is not complicated in principle. Iron oxide, present in the magma, can react with hydrogen to produce water. The reaction is iron oxide plus hydrogen yields metallic iron plus water. The water produced either escapes into the young atmosphere or gets dissolved into the magma. As the planet cools and the magma solidifies, the water trapped inside begins to release through volcanic outgassing. Over hundreds of millions of years, volcanoes pump water vapor into the atmosphere. The vapor condenses, rain falls, oceans form. In this model, the water on Earth is not foreign material. It is a byproduct of the planet's own formation chemistry. Earth didn't receive water. Earth made water. This idea was theoretical for years. In 2025, Francesca Miozzi and Anat Shahar of Carnegie Institution for Science, working with colleagues from Paris and UCLA, ran the first laboratory experiment to test it directly. They built a miniature version of a young planet. They took iron-rich silicate melt, the kind of material that would have made up Earth's magma ocean, and exposed it to molecular hydrogen at extreme conditions. 600,000 times atmospheric pressure, temperatures above 4,000 degrees Celsius. They used two diamonds pressed together to create a microscopic chamber that could hold these pressures. Then they heated it with lasers. Inside the diamond cell, hydrogen reacted with the molten rock. Water formed. For the first time, in a laboratory, scientists watched hydrogen and magma chemically combine to produce water, not absorb it from outside, but generate it through reaction. The implications are significant. If water formation is a natural output of the planet-building process, not a lucky delivery from space, but a chemical consequence of having iron-rich magma and a hydrogen atmosphere, then water might be common on rocky planets throughout the galaxy. Earth's oceans might not be a cosmic accident. They might be inevitable. Shahar's team notes the timing works. The solar nebula dissipates within a few million years of solar system formation. But iron meteorites, the oldest differentiated objects in the solar system, date to just 1 or 2 million years after formation. The magma ocean stage overlaps with the nebular stage. The window exists. Each theory has a problem, and the problem is always the same: the chemical fingerprint. Water has a traceable signature. The D/H ratio, the proportion of heavy hydrogen to ordinary hydrogen, records where and how water formed. Cold, distant environments produce higher deuterium ratios. Hot, inner solar system environments produce lower ones. Earth's oceans have a D/H ratio of 1.56 times 10 to the minus 4. Oort cloud comets, roughly 3 times 10 to the minus 4. Too high. Some Jupiter family comets, close to Earth's ratio, a potential match. Carbonaceous chondrite asteroids, close to Earth's ratio, another potential match. The solar nebula hydrogen that Shahar's model uses, lower D over H than Earth's oceans. This means that if Earth made its own water from nebular hydrogen, the resulting water should be lighter, lower in deuterium, than what is actually in the oceans. Something must have added deuterium. Either late asteroid impacts topped up the oceans after the magma ocean stage, or the nebular hydrogen wasn't as light as scientists currently estimate, or the picture is more complicated than any single model. Most scientists now lean toward a combination. Karen Meach, an astronomer at the University of Hawaii who has studied cometary water for decades, put it this way in 2026. The water in Earth's oceans is probably a cocktail, multiple sources, mixed over hundreds of millions of years, then filtered and transformed by billions of years of geology, volcanism, plate tectonics, and biology. The cocktail theory doesn't make a clean story. It makes an accurate one. There is another angle that most summaries skip. Earth hasn't just been receiving water and keeping it. Earth has been cycling water for billions of years through a mechanism that is more active and more violent than most people realize. At mid-ocean ridges, the places where tectonic plates pull apart, seawater seeps into cracks in the ocean floor and gets pulled down into the hot rock below. There, at extreme temperatures, it reacts with the rock, changing its chemistry, and eventually gets recycled back out through hydrothermal vents or subducted down into the mantle. At subduction zones, where one tectonic plate slides under another, water-soaked oceanic crust dives deep into the mantle. The water gets squeezed out under pressure, rising up through the overlying plate and triggering volcanic eruptions. That water goes back into the atmosphere. Some of it gets recycled into the ocean. Some gets locked into new rocks. The water cycle most people learn in school: evaporation, clouds, rain, rivers, ocean, is a surface phenomenon. But there is a deeper cycle, running through the solid rock of the planet, operating over millions of years. This deep water cycle means that some of the water in Earth's oceans has been through the mantle. It has been chemically transformed, isotopically modified, and returned. The oceans are not a static reservoir. They are part of an ongoing exchange between the surface and the planet's interior. How much water is currently in the mantle? Estimates vary, but some research suggests the mantle may contain more water than all the oceans combined, locked in minerals like olivine and ringwoodite, which can hold water in their crystal structures at high pressures. The discovery of a hydrous mineral called ringwoodite in a diamond brought up from the mantle in 2014 provided direct evidence that the mantle's transition zone, at a depth of 410 to 660 kilometers, may be extraordinarily wet. The water on the surface is not all the water. The planet is holding more, deep down, in forms that aren't liquid, not yet. If Earth had liquid water early, very early, there should be evidence in the rock record. The oldest surviving materials on Earth are not rocks. They are crystals. Specifically, zircon crystals from Western Australia, a place called the Jack Hills Formation, that have been dated to 4.4 billion years ago. These crystals formed only 150 million years after Earth itself, and they contain a chemical signature of liquid water. Zircon forms differently depending on whether it crystallizes from dry magma or wet magma, magma that interacted with water. The oxygen isotope ratios in Jack Hill's zircons suggest that by 4.4 billion years ago, Earth had liquid water at the surface. The planet was wet within its first 200 million years. That is remarkably fast. The Late Heavy Bombardment, the asteroid impact event that many models invoked as the main water delivery mechanism, didn't peak until 4.1 to 3.8 billion years ago. If the zircons are right, liquid water was present on Earth before that bombardment reached its peak. This creates a timing problem for the pure asteroid delivery model. If asteroids were the primary source, why was Earth already wet before the main bombardment? Either some other delivery mechanism was faster, or Earth was making water on its own through the magma hydrogen chemistry, or the late heavy bombardment's timing is being misread. In 2024, another study of ancient zircon crystals found that Earth might have had freshwater continental systems, not just salty ocean, very early in its history. The chemical signatures in the crystals pointed to granitic continental crust interacting with meteoric water that fell as rain, by 4 billion years ago. A very early rain cycle on a very young planet. The rocks are not giving simple answers. They are giving layered ones. Understanding where Earth's water came from becomes clearer or stranger when viewed from other planets. Mars once had liquid water. The evidence is all over the Martian surface. Ancient riverbeds, delta fans where sediment accumulated, minerals that form only in the presence of water. 3 billion years ago, Mars may have had a shallow ocean covering its northern hemisphere. Today, Mars is a frozen desert with only trace amounts of ice buried at the poles and locked in subsurface deposits. What happened? Mars lost its magnetic field early in its history. Without a magnetic field, the solar wind, a constant stream of charged particles from the sun, could slowly strip away the Martian atmosphere. Without an atmosphere, surface pressure dropped. Without surface pressure, liquid water cannot exist. The water either evaporated into space or was chemically locked into rock. NASA's Perseverance rover, which landed on Mars in 2021, has been studying the chemistry of Martian rocks and soil for evidence of this ancient water story. In 2025, new analysis of Perseverance's data identified multiple mineral-forming events in the subsurface, products of water interacting with rock at different periods in Mars's past. The water history of Mars is layered and complex. Venus tells a different story. Models suggest that Venus may once have had liquid water as well, a shallow ocean, perhaps for the first billion years of the solar system's existence. Then a runaway greenhouse effect took hold. The sun warmed Venus enough to evaporate its oceans. Water vapor, a greenhouse gas, trapped more heat. More heat evaporated more water. A feedback loop accelerated until the surface temperature reached 465 degrees Celsius, and the oceans were gone forever. Earth sits in the middle. It has a magnetic field. It has plate tectonics that regulate carbon dioxide levels over millions of years. It sits at the right distance from the sun. Earth kept its water. Mars lost it to space. Venus boiled it away. The water was always secondary to the question of whether a planet could hold it. In 2024, a French research team led by Quentin Krall published a theory that bypassed impacts entirely. Most delivery models assume that water arrived on Earth through collisions, comets, or asteroids slamming into the planet. But Krall's team proposed a different mechanism: gas phase delivery. In the early solar system, gas from icy objects beyond the snow line, the boundary in the solar disk where water ice becomes stable, could drift inward toward the sun through a process called Poynting-Robertson drag, combined with photodesorption, where solar radiation lifts molecules off the surface of icy dust. These water molecules, in gas form, could be carried inward by the disk's dynamics and absorbed directly by the young rocky planets without any collision at all. This model is called impact-free delivery. It relies on the chemistry of the protoplanetary disk, the rotating cloud of gas and dust from which the planets formed, rather than on individual impacts. Water seeps in like fog, not like a flood. The advantage of this model is that it avoids the timing problems of impact-based delivery. The disk is present from the very beginning of planet formation. Gas phase water delivery can begin before any comets or asteroids reach the inner solar system. The disadvantage is that the model is hard to test directly. The protoplanetary disk is gone. The evidence it left behind is indirect. But the idea represents a shift in how scientists are thinking about the problem. The question is no longer just, what hit Earth? It is, What did Earth absorb from the space around it while it was forming? A two-word chemistry lesson, because it changes the picture. Water is H2O, 2 hydrogen atoms, 1 oxygen atom. Hydrogen is the most abundant element in the universe. It has been present since 3 minutes after the Big Bang, when the universe cooled enough to let protons and electrons combine. Oxygen is made in stars, in the nuclear furnaces of massive stars, then scattered through space when those stars explode as supernovae. When hydrogen and oxygen meet under the right conditions, they form water, and the universe is full of water. There is water ice on asteroids, on comets, on the moons of Jupiter and Saturn, in the dust clouds between stars. Water is not rare in the cosmos. It is one of the most common molecules in existence. This reframes the mystery. The question is not, how did water get to Earth, as if water were a scarce commodity that had to be imported. The question is, why did Earth retain water when its neighbors didn't? The water was always nearby. The universe was soaking in it. The challenge was keeping it. A planet too close to its star loses water to stellar radiation. A planet too hot loses water through atmospheric escape. A planet too small lacks the gravity to hold a substantial atmosphere, which means it can't sustain the pressure needed for liquid water at the surface. Earth threaded all of those needles. Not perfectly, Earth has lost some water to space over billions of years, and will continue to do so, but slowly enough that the oceans have persisted. The water's origin is one question. Earth's fitness to hold it is a separate, equally interesting one. As of 2026, here is where the science stands. No single theory explains the full chemical composition of Earth's water with perfect accuracy. The D/H ratio, the isotopes of oxygen, the abundances of other volatiles like nitrogen and carbon, all of these carry signatures that point in slightly different directions. The leading framework is a mixture. Earth formed with some hydrogen already present in its building blocks. During the magma ocean phase, that hydrogen reacted with iron-rich rock to produce water. This gives a baseline, a foundational layer of water that Earth generated itself, before any external delivery. After that, water-rich asteroid impactors, particularly carbonaceous chondrites from the outer asteroid belt, brought additional water during the first 500 million years of Earth's history. These impacts added to the oceans, and also contributed volatiles that adjusted the isotopic signature. A smaller contribution may have come from comets, particularly Jupiter family comets with D/H ratios close to Earth's. Comets may also have brought organic molecules alongside water, a detail that has implications for the origin of life. The magma ocean outgassed water continuously as it cooled, contributing through volcanism. The result is not a single clean origin. It is a palimpsest, layers written on top of layers, each leaving a faint trace that scientists are now painstakingly reading through meteorite analysis, spacecraft measurements, ancient crystals, and diamond anvil experiments. The most striking development in recent years is that Earth itself, its interior, its chemistry, its early geological processes, is now a serious candidate as a water source. Not just a receiver of water from space, but a generator of water from its own materials. That changes the story considerably. The question of where Earth's water came from is not an academic curiosity. It is directly connected to the question of life. Life, as it exists on Earth, requires liquid water. Every living cell depends on water for chemistry, for transport, for the reactions that make metabolism possible. The origin of life on Earth cannot be separated from the origin of water on Earth. The two histories are the same history, and the question of water's origin on Earth has implications for every other planet in the universe. If water arrived on Earth purely through random asteroid or comet impacts, an unlikely coincidence of orbital mechanics, then water-bearing planets might be rare. Life might be rare. The universe might be mostly empty in the ways that matter. If water forms naturally on rocky planets as a byproduct of the magma ocean and hydrogen atmosphere chemistry, if it is an inherent consequence of planet formation, then water-bearing planets might be common. Every rocky planet that forms inside a gas disk, every world that goes through the magma ocean stage, could be wet by default. Life might be common. The universe might be full in ways that matter. The Carnegie experiments, published in 2025, lean toward the second picture. If the magma-hydrogen reaction is a universal feature of rocky planet formation, and if the most common type of planet in the galaxy, the sub-Neptune, goes through exactly that stage, then water production might be baked into the very process of planet making. That is a significant shift from water was delivered to Earth by chance to water forms wherever the conditions are right and the conditions are common. The oceans on Earth might not be a miracle. They might be a default. One more layer, and this one is easy to miss. The water in Earth's oceans is old. Some of it is very, very old. The hydrogen atoms in water were forged in the first few minutes after the Big Bang, 13.8 billion years ago. The oxygen atoms were forged in massive stars that lived and died before our sun even existed, scattered into space when those stars exploded. Then the atoms drifted through interstellar clouds, accreted into the protoplanetary disk around our young sun, became part of asteroids or comets, or the building blocks of Earth, went through the magma ocean, outgassed through volcanoes, fell as rain, joined the ocean, cycled through the biosphere, evaporated, fell again. The water molecule that was in the rain outside a window last Tuesday may have been inside a dinosaur 80 million years ago, may have been part of a glacier 20,000 years ago, may have passed through the bloodstream of a fish 200 million years ago, may have sat in a comet for 1 billion years before that. Water is not static. It is one of the most active substances on the planet, constantly cycling, constantly moving, constantly changing context while remaining chemically unchanged. H2O, the formula that built the ocean, the formula that makes up 60% of a human body, the formula that makes Earth visible from space as a blue marble. And after billions of dollars of spacecraft, decades of research, zircon crystals from 4.4 billion years ago, diamond anvil experiments at 600,000 atmospheres, and probes chasing comets across the solar system, the answer to where it came from is probably the planet made some, and space delivered the rest, and we're still working out the proportions. That is the honest answer. It is also, in its own way, a more interesting one than any clean origin story would be.